And today we're going to have Ismail, who is the co-founder and CSO of GuideLabs, which is a really cool startup in the Bay Area working on interpretable LLMs. And very rightly so, and sort of appropriate to this sort of series, she's going to be talking today about some of the work that they've done specifically in scaling up inherently interpretable models to the scale of large language models. So yeah, please, Haya, take it away.
Thank you so much. Please do interrupt me if you have any questions in the talk. Okay, so today I'll be talking about Steerling-8B, which is our first LLM that we scaled up to 8 billion parameters. So I'm going to start with like this prompt, which is a prompt we gave our model, and it says how to get rich, and then we have regularly what the model would respond, and then on the right is basically what we got as an output when we amplified the concept of book publishing. And if you look at both examples, what you'll find is like the one on the left just talks about like regular information, educate yourself, build a strong foundation, invest wisely. But the right, it's mainly talking about publishing. It has a lot of reference about books and like which books might help you basically become rich. And this is like basic. And throughout this talk, I'll be talking about how we made an architecture that basically allows us to make this kind of behavior. So I'm going to start with how like frontier labs train language models these days. And it's usually in this kind of format. Well, we get a lot of raw data. Usually it's going to be from the web. Then they create a large transformer or a mixture of experts. And then they start pre-training. Then they do mid-training. After that, they do long context extension. Then they start to do reasoning, which is done like by SFT or RLVR. Then they instruction tune the model, then they align the model, then it's their production model. And that's how typically you would build an LLM. And this is an example from the ALMO3 paper where they showed this exact steps. So they pre-trained, mid-trained, long context extension, and then turned it into a thinking model via training for reasoning and an instruct model. So this is like a very typical workflow. After that, what people try to do is after the model is trained, they try to look into the production model and try to interpret the model and try to understand what the model learned. How can we steer the model? How can we debug the model? Can we fix the model? What did it understand? And they start like basically poking around into that model itself. But that's a problem because you end up getting things like this, which is, well, people come up with interpretability methods, for example, sparse autoencoders, which they're supposed to use to understand the different neurons in the neural network, but then they become unreliable and people think they're seeing something, but it's not. Other people like say, oh no, this is not reliable. And there becomes this debate of whether what you are actually getting out of this different interpretability methods is actually true or not. And the same thing happens with reasoning. Is our chain of thoughts faithful? Is the model actually telling us what it's doing? Or is it just like hiding things? And that becomes a whole big area of research just to understand if the ways we're looking at the model's explanation are actually real or not. So I think the main problem that keeps on happening is because what happens is that people think about interpretability as an afterthought rather than a process, part of the process. So when we decided people came up with reasoning model, reasoning didn't really emerge, right? People trained models to reason. So far, what have been happening in language models is people have not train model to be interpretable rather than take a model and try to interpret it. And that's kind of has been the problem. And that's the problem I'll be trying to address through this talk. So if you basically think about interpretability throughout the whole process, to make a model interpretable, language model interpretable, first you would take your data, but that's not enough. You would need to annotate it with some human understandable concepts, because you would want to know how to learn these concepts. So first you need to annotate the data with that. Then you would have to modify the architecture to make sure that it can support different modes of interpretability you want. Then you, throughout the whole training process, as long as you're doing any part of training, through it, it's pre-training, mid-training, SFT, or even RL, you would need to consider interpretability losses in your loss objectives. And if you do that, basically you get something that's much easier to interpret, easier to understand, and hopefully overall more useful in terms of interpretability. So the style of this talk is going to be, we made a lot of changes in this whole pipeline, as I just showed. So it's going to be what change we made, how we made it, and why we made it. And again, feel free to interrupt at any time. So I'm going to start with the data. So for the data, we did two things. We did training data annotation, and we did training data indexing. So for the data annotation, what we took is we took our entire training corpus, and which was 1.35 trillion tokens, and we annotated them with a 33,000 human understandable concepts. Okay, so our annotation pipeline is composed of the following. First, we took a sample from this corpus, and then so it was like a small sample, and then what we did is that we chunked this corpus, which means that we took each document and made it into smaller pieces of text. And then after that, we asked Mistral a Mistral model to basically tag each text and tell us what this text is about. And we ended up with 14 unique tags from this 6 million documents. So after that, we took these tags and we did some sort of filtering process to get concepts from them. So we did that by first we clustered them, and then after that, so we ended up with different cluster centers. We came in clustering, and then from every cluster center, we did a lot of filtering to find and deduplication to find clusters that are somewhat meaningful. And then that's how we ended up with 33,000 concepts, which are 33,000 clusters that we found after pruning and deduplication. And then what we did is we took this data and used it as a training data set for a model. So we started from an LLM, and we treated this as like just like, are these concepts present or not? Since here, this is a positive unlabeled training problem, which means that we only have positive labels. So we only, for a given sentence, we only know that this concept is there. We don't not necessarily know that the concept is not there. So we used a PU loss, and basically we made a pass on our entire training corpus, so that every chunk is annotated with at least 16 of these concepts. So, okay, why did we do that? Because we really wanted a data set that looks like this, which is basically a piece of text that has chunks and denoted by our end of chunk token, which is our EOC, and every chunk is annotated with a set of concepts so that later we can use this for training the model itself. So this is the first thing we did with data, which is data annotation. The second thing we did is data indexing. So basically, we took all our pre-training data and we indexed it after chunking. And how we did that is we took the pre-training corpus, we chunked it, and we embedded it into an embedding model, and then we indexed every embedding using a fast index, which is Facebook's indexing search package. And then why we wanted to do that is because we know that during inference, our model is going to generate something. So we wanted to know what training data was closest to this model. So if you index all the training corpus and then during generation you generate something, then you can just do some simple k-nearest neighbors search on the top documents with this index and just find the document that is related to this particular index. So then you kind of know which training data was most related to the output by just doing a simple k-nearest neighbor. So that was mainly what we did for our data. Next, we made changes in the architecture. So typically when people train language models, the default choice is basically autoregressive models. And this is like most of the frontiers labs like OpenAI, GPT is an autoregressive model, Claude is an autoregressive model, but there are other types of models. So one type is a diffusion model, which came out, the first diffusion language model that came out for production level is called Mercury from Inception Labs. But usually what people would do is just train an autoregressive model because we know all the hyperparameters for it, and it's very well studied at this point. But basically, we decided we're not going to do that. We're going to train a causal diffusion model with a concept module. Okay, so first, let's talk about the causal diffusion part. An autoregressive model is a model that you give it a sentence and it basically predicts the next word in the sentence. It's trained to do that, and that's how most of the language model historically have been trained, are just predict the next word. They scale very well. We know all the hyperparameters for them. We know we have very well-studied scaling laws for autoregressive model, and we know that they work quite well because we've been using them for a few years now. Okay, the other type is the diffusion language model. Diffusion language model, there are different types. Here I'm showing a type that is called mask diffusion, which is you start from a noisy sequence, which is all mask, and then you slowly unmask some of it. So you start with all mask, and then you have the sat mat, for example, and then you continue to unmask until you have the full sentence. This is one type of diffusion model called mask diffusion model, but there's other types as well. But this is the type I'll be mostly focused on. So autoregressive models typically have a causal attention mask. So every token, you attend to all the previous token, but you never see the future. Diffusion models have usually a full attention mask, which means every tokens can see every other token. But there are variants of that, one of which is called block diffusion, which means that, well, the noisy tokens, the one that we did not have, we did, like the ones that we still didn't predict, can basically see everything before it that is clean, but cannot see anything in the future. And this is why it's called block diffusion. So here um, the third image, you would see that the attention mask is the purple part. So for example, if you are here, then if you are like in the second block, in the first block, you can see the block before you, but you can't see anything afterwards. So you can attend to everything previous to that has already been masked, but you can't attend to anything afterwards. So the problem with this block the block diffusion one, is that basically you need 2x the context size. So it's very expensive to train because you have to have the clean part to make sure that like when you are training, you have access to the clean part because you want to see that from previous blocks. And you also have the context list that you are trying to decode from. So that makes it very, very expensive. So when we were trying to figure out how to, block causal made sense for us because it's somewhere between pure causal attention and like full attention. And in the same sense, we have this notion of chunks where you can think about a chunk is like a few blocks. So it made more sense for us to go with something similar to block diffusion, but at the same time, this clean and noisy sequence appended to one another seemed very expensive in training. That means your training cost is 2x. So one thing we noticed that you really don't need the clean signal. So if you train with just noisy signal and have block causal attention, which means that you can, within the block, you see that block, you see previous noisy blocks, but you never see the future, then basically what you get is the same effect as a block diffusion without actually having the clean part, so it's much cheaper. So that is kind of what we ended up going with, which is like a diffusion model with this causal block attention. And the reason why we chose this was for two things. First, diffusion models have masks, which means that when we want to do input feature attribution, we can do that faithfully because we already added noise during the training process. So when we're measuring the change of an input from a noisy distribution, we can do that because that was our training process. And autoregressive model, you don't train them with noise, so you really don't have such a baseline. The other thing is, in principle, one thing that makes diffusion models very attractive to people, and that's why if anybody tried the Mercury model, they'll find the most impressive thing is like it's super fast. It's much faster than any other model, is because it can generate multiple tokens at a time. Yes, the quality of these tokens are not great as like autoregressive models, but you can basically parallelly generate more things. So when we were starting to think about the idea of we want a language model that has concepts and that we can control for these concepts and can generate, we thought, okay, well, concepts don't necessarily exist in a single token. They exist in multiple tokens, so maybe it makes sense to have something that can generate multiple tokens at a time. That said, so this part you can take a little bit with a grain of salt, because like when you generate multiple tokens at a time, the quality gets harmed. So people usually end up generating one token at a time, unless you figure out a good way to kind of do that, which is, I guess, the Mercury people figured that one out. But yeah, so this is the reason why we decided to go with a causal diffusion model. Okay, so the second change we made to the architecture is adding a concept module. And what that looks like, usually you would have your input, you pass it through a transformer, you get a hidden representation. That hidden representation, you pass it to the language modeling head, and then you get an output. So what we did is we took this hidden representation and we decided we're going to pass it through what we call a concept module. So to do, first you take this hidden representation, you pass it through a function that predicts the known concept. And it basically, what this function says is, okay, I think these concepts have, I think this hidden representation has these concepts. And then you get an activation per concept. So our model, if you have 33,000 concepts, you get 33,000 activations that says if a concept is present or not. So you take these activations, you multiply them by embeddings that represent the different concepts, and then you basically get the embedding, that the concept embedding. And here, just for a caveat, since I mentioned we have like 33,000 concepts, you actually don't do this you sparsify it somehow. So we do that by applying top K. So we only take like the top concepts to make sure that like we don't end up with 33,000 representation summed together. So yeah. So this basically gives you the known part of the of our hidden representation. You do the same part, but here you pass it through another head, which we call the unknown head, and then you get activations for concepts that we don't really have labels for, but they do exist. And then you do the same thing. You have embeddings that represents these concepts. And then you multiply that, and then you get this UAT, which is your unknown embedding. But there is then one more thing you might want to do. So you can think about this as a decomposition, right? You took this hidden representation, you decomposed it into a known part and an unknown part, but there's a lot of things that might be lost and might affect quality. So you might want to consider adding that back in, which is basically what we call the residual, which is whatever that was left from the decomposition. This is, yes, black box, but we're going to train it to basically try to minimize it. And at least during inference, when we do get signal from this, we can always turn it off. And we did do that, and it does affect slightly generation, but not that much. So if somebody would want to say, oh no, I don't want anything from the residual path, you can just always turn that path off and just get the decomposition from the known and the unknown. So after you have these three embeddings, you basically sum them up, and then you get the hidden representation again, which you already had, and then you pass through the LM head, and you get the output tokens. So why we wanted to do that, because basically we wanted to take any token we output and decompose it linearly into a set of known and unknown or a discovered concept and a residual. And so that like when we are generating, we know like the different concepts that were activated during this generation and how much the model relied on some things that were not from the concepts. And this linear decomposition allows us to do that. Okay, so this is the architecture part. After that, I said we were going to basically start training for interpretability. And so I'll talk about that. Yeah, if anybody has any questions, it's a good time to stop me, but if not, I'll just continue. Okay, so here, basically, what I mean is that we are going to add interpretability losses in pre-training, mid-training, and SFT. And the first obvious loss that we're going to have is is a concept loss, which means that I talked at the beginning and I said, okay, we annotated this data with a set of concepts so that live throughout a chunk. So the chunk has these concepts in it, but we don't know exactly which the concepts were in which token. So here what we do is we have a binary cross entropy across the whole chunk, which says with an OR operation, which basically says if any of the tokens within the chunk happen to have this concept, then okay, then we can say that the chunk has this concept and the losses goes down. But if they don't, if the entire chunk does not have the concept, then the loss basically goes up. So it's a binary cross entropy. It's just a regular cross entropy loss, but it's now across the entire chunk rather than on a given token, because the way we annotated the data is that the whole chunk might have a concept rather than a single token. But at the end of the day, we're predicting tokens. So this is kind of like how you would navigate that. So the first loss is just a concept loss. The second loss is basically we call an independence loss, which is a cross-covariant penalty between the known and the unknown, which just tries to minimize the information for a given batch that is between the known and the unknown, and it does that by minimizing the cross covariance between the activations for these two embeddings. So basically what this does is kind of encourages the disentanglement between the known and the unknown concepts and prevents the known head from basically duplicating the unknown head from duplicating the things that is already trained in the known head. And if you like remove this loss, then you get things that are like that really don't make sense in concept space. So it turned out that this loss is pretty important. So this is the second loss we have. And then the third loss we have is a reconstruction loss for the unknown part. So for the known part, we said we have the concept loss, which makes sense because we have labels. So when we have labels, we can just say, okay, is this concept there or not? But for the unknown, we said we take the embedding and we decompose it, but we don't really have ground truth for that. So what is the ground truth for the unknown if we don't have unknown labels? So here we said the ground truth is basically whatever was in the hidden representation that is not in the ground truth known. So then basically what we do is we calculate the actual known, which is from the ground truth labels of our concepts. So this gives us the actual known embedding, and then the actual unknown embedding is whatever is remaining into the hidden from the hidden representation that is not in this known embedding. So, and then we minimize the loss between whatever the decomposition gave us, which is u hat, and the whatever should have been there, which is the difference between the hidden representation and the known. And we try to minimize this. And if you think about this, if this goes down to basically 0, then this residual connection that we showed would have 0 effect because everything would perfect decomposition of whatever that was not captured in the unknown head would be in the known head would be captured in the unknown head. So yeah, so that is our third loss. So now if we put all of these together, we of course have the regular language modeling loss, which is the token loss, and this is for mass language model, it's just cross entropy on the mass token. Then we have the concept loss, our independence loss, and the reconstruction loss. Okay, so why did we do this? We needed all of these losses because basically if you take this architecture and you don't add any losses, then the model really doesn't deliver on any of its promises. So the concept loss helps you make sure that the concept embedding actually embedding the concepts we want, and that the concept head learns concepts. The independence loss makes sure, or here it's also the Hisik loss, because it is the linear Hisik loss with a linear kernel, and it basically allows you to disentangle the unknown and the known from each other, to kind of like promotes disentanglement. And then the reconstruction loss to make sure that this residual is zero, and then that like the unknown head can absorb everything that is not in the known. And then of course the language modeling task, which is our main objective. If you so you end up with like the different losses, and you add these losses in every stage. So you have them in pre-training, on that training corpus, you do that on mid-training, you do that on supervised fine-tuning and instructing tuning your model and everything. Okay, so we did all of this on a large scale, which is 8 billion, and we ended up with a model we called Steerling-8B. So Steerling is our, I guess, to our knowledge, is the first like inherently interpretable model, in the sense that trained from scratch, because there are models that people try to add concept bottlenecks that were like take a pre-trained model and fine-tune it. But here we trained it from scratch. We have 33 known concepts that we had labels for. And then we said, okay, how many unknown concepts are we going to have? So we just did 3x of that. So we have 110 discovered concepts. We trained, we pre-trained on 1.2 trillion tokens from Nemotron HQ, and then we mid-trained on 150 billion tokens from the OLMO2 mid-training data mixture. Currently, our base model is on Hugging Face. We have replicated LADA's SFT procedure. So our instruct model is also ready and will be on Hugging Face soon. And we will be releasing a technical report with like all of the details about the model and how we trained it, like in a month or so. Okay, so how does Steerling perform in compared to like other models? So this is kind of like different Steerling in comparison to models of the same size. So the x-axis is the flops. So I mentioned that Steerling was trained on 1.2 trillion pre-training and 150 billion mid-training, which is really, really small in comparison to how much people train these days. So for example, Llama 3, 8B was trained on 15 trillion tokens, which is 15, I mean, it's like a lot more than what we trained on. So you can imagine that that's going to have a huge effect. Our closest model is LADA, and LADA is also a diffusion model, not a causal diffusion model. It's a diffusion model, but LADA here was trained on 2.3 trillion tokens, and again, Steerling was trained on 1.2. So if you look flop-wise, Steerling was like an order of magnitude less than everybody else. Performance-wise, it's not like the best model in terms of LM harness accuracy, but it's very compatible also compared to the amount of training that actually went into this model. So this is kind of like how we do in LM harness, and this is the average across 7 benchmarks. Okay, so we did all of this work, and so what did we get out of it? Like, what does Steerling allow us to do that you can't do with LADA, or you can't do with Llama or Olmo or other models, or the DeepSeek models? So basically, it allows us a few things that we thought were pretty cool and worth going through all this pain. First, faithful input feature attribution. We can get concept attribution and steering, and then we can also learn something about and we can get insights about what the model actually learned. So let's talk about like faithful input feature attribution. And in the beginning of this talk, I mentioned that like we chose a diffusion model because you have masking, and then when you have masking, you can just use integrated gradient to find the important tokens in the input that basically push the output. So this is covered, but the idea is like if you had a text that says what is Mary's job, and then you want to, and then use the model outputted a nurse, and you want to know which logics was, which token contributed to the output, which is the nurse the most, then if you can just do a single step integrated gradient, and that will tell you which, like if Mary is the most important word that contributed to the output. And since you already, what you do is you compare the with the word Mary or with the mask instead of Mary. And if there's a large score, then this says basically Mary affected the output a lot. So Mary is the most important word for the output. And this is an example from our model where we gave it a prompt about gene editing, and it outputted like things about DNA and genomics. And then when we looked at the input features, okay, why did it output this particular things? We found that the word gene was important, the word editing was important, nucleus was important, and these were the tokens that the model mostly depended on to generate this particular output. So that's what I mean by like input feature attribution, is like which part of the input depended on the output. So yeah, so that's one thing we can get. The second thing is concept attribution. And if you like recall a few slides ago when I was talking about our architecture, I said basically what you have is you have these alphas that represent the presence or the absence of the different concepts, either known and unknown. And you multiply that by the embeddings, and then you get your distribute your like new representation. So one thing you could do is when you're generating a chunk, you can look at every single token you generate, and then you can look at the scores for every single one, and then you can aggregate them. And then at the end, you can output to the user the top concepts that were used in this entire chunk to generate a particular output. And then again, with our DNA example, if you do that, you'll find that like, okay, sometimes the most important concept can be like clinical, analytical, professional, genomics, biological chemistry process, and so on. So this is like how the concept appeared across the whole chunk. Noting that this is like, again, every token has a ton of concepts, and then if the chunk becomes really long, then maybe the concept contribution can be diluted, but at least we can tell for every token itself also like where the like what are the most important concepts that affected that particular token. Okay, another application that you can get through this is steering. So there are different types of steering. There is like causal concept intervention, which there is a concept application and a concept suppression. So this is the base case where you have a mask, you pass it through our model, then you have alpha times instead of known concept, alpha times instead of unknown concept, and residual. Then you use that to get the hidden representation, and then pass it through the LM head and get the prediction. So if you would want to basically make sure that you generate that particular concept, that's really easy, right? You'll just set that concept to be on and everything else to be off. You'll get the concept generated, but that will just kind of, you won't get anything fluent or coherent at that point, because there is really, the model has no option except to sample from that concept distribution. Because now, instead of having like the entire vocabulary, it just, you can think about it as if you are shrinking the vocabulary to a set of tokens that are related to this concept. It will give you exactly the concept output, which might be useful in some cases. So this is like a causal intervention. It will always succeed, but it won't generate because like it won't generate something fluent, because you set alpha for this only this concept to 1 and everything else to basically 0. Another way you could do this is you can do something similar to the steering vector literature, which is you take the embedding, this concept embedding, and you add it to the middle layer of the transformer and say, okay, well, I don't want to set it alpha to 1 for this concept and everybody else to 0. I am going to add alpha to a middle layer of this transformer, and I'm going to add like the embedding to the middle layer of the transformer, and then let the transformer like decide on the value of alpha. And when you get this, you kind of like push the model towards this the concept that we wanted to output. And yeah, that is another way you get something coherent and fluent. And then there is concept suppression, which means that, okay, I don't want to output this concept. So one thing you could do is you can just like subtract the concept from the output before you pass it through, like pre-generated to the user. So any tokens that come from this concept, if you subtract it, then you basically end up with like this, with like removing the concept from the output, basically. So this is a way you can suppress the concept as well. Okay, so this brings us back to our example that I talked about in the beginning. So here in this example, we wanted to do like steering. So we use the second part where we added the concept embedding to the transformer and let the model figure out the values of the alpha. So it generated something like this. I had a live demo that I wanted to share, but I'm running short on time. So I'll just share the link on the chat when I'm done, and people can try the model, the SFT model, and steering on it for themselves afterwards. Okay, so I'll try to be quick for whatever is remaining. But here, so one question that is really interesting for us was like, what did really Steerling learn? And we can do that by basically inspecting and labeling the unknown concepts. And it's really easy, right? You can just take the concept embedding, multiply it by the LM head, get the top tokens, and then look at them and see, say, okay, what are these top tokens, and what do they like promote? And then you can also do a second step where, since there are 100,000 concepts, you can just pass them through an LLM, ask it to label these top tokens. So we did that, and we found really cool concepts. So there is an EM dash concept, which basically I'm sure a lot of you using like Claude always notice that it always does the EM dash, and apparently it's a concept that the model learned very clearly as one of this discovered concept. There is a second person pronouns across languages. So there is you across different languages. So that's another concept. And there is also things like conditional like if, when, where, since, and that's another concept. So it's kind of very interesting to see these different tokens that got latched to like unknown concept embedding. And one thing we found that we were trying to play with the model is that you can actually give it its concept embedding as an input token and ask it to generate. So this was with the base model, not the SFT. So I made it as if you're generating from a base model. So my prompt was, today let's explore the idea of, and I just grabbed something from the concept embedding and I just add that. I never actually like supervised or fine-tuned or did anything. I just like said, okay, if I give the model its actually internal representation, let's see what's going to happen. This was inspired by like machine language, a paper that Ben Kim wrote previously, but yeah. So what happened was that like when I injected this concept that was related to gene expression, without the injection, the model, let's talk about, it said subgroups and like toys and boxes. But when I added this, its internal representation, which is the concept embedding, it talked about gene therapy, gene treatments, and it was very fluent. So that was very interesting to see that the model can actually describe its internal concept if you give it to it as an input. So yes, just to recap, so we built Steerling-8B. It's an inherently interpretable model, trained from scratch. It's compatible to like other 8 billion size model, trained a lot less. So take that into consideration. It allows us for attribution, for concept attribution, feature attribution, training data attribution, concept steering, and model can kind of like talk about itself and explain its behavior. The base model is already on Hugging Face. The code is open for people to try out. The SFT model and the technical report are going to be out soon. So yes, this is the Guide Lab team, and I'm going to stop here and happy to take any questions. I'll also put the link for our for if people want to like play with the model, I guess, in the chat.
Amazing. Thank you so much, Saya. Amazing talk. Does anyone have any questions? Yeah, actually, go for it.
Yeah, hi, Aya. Thanks for the great talk. Yeah, it's really interesting to see that, like, if you give the concept embedding to the model, like, it's still able to understand it. Like, that's like one sort of limitation that people talk about, like concept embeddings are sometimes uninterpretable, and so that's really nice. So, like, what do you think about like have you checked like if the concept embeddings are sort of converging to the LLM embeddings or something, or if you like actually try to enforce the concept embeddings to also follow the LLM embeddings, would that work?
So this was something kind of like what we did in the end. I think so. This was inspired by Ben Kim's work on basically there was a paper that she was talking about that like language models, machines have their own language, and she was trying to doing fine tuning or like DPO, I think, to basically try to understand what different representations mean to the machine itself. So that basically made me say, okay, what happens if we just give the concept embedding? I think if we like do some sort of supervised fine tuning to force the models to talk about the concept, if we give it the embedding, that will even work even better. But like here, I was just giving the embedding as an input token. At the end of the day, the embedding is correlated to the output rate because it's like right before the LM head. So you can, it's correlated to a set of top tokens, not a single token itself, but top tokens and the weights between the tokens and the LM head, like we do weight sharing. So they're tied. So I think that's why it might have worked. Is it like perfect? Does it always talk about it's not a perfect process sometimes, like, but also this was a base model, so maybe the instruction tune model would do better. But it is, but yeah, but it was very different. Definitely interesting to see, and I think it worked because the concept embeddings are basically tied to a set of tokens, which are the top tokens that they promote. So when you, although it's not a single token, but you're kind of saying, talk about this set of tokens, so the model talks about them. Yeah, so that's kind of like what we found.
Yeah, thanks.
Pietro, I think you have a question.
Yeah, thank you so much for the talk. First of all, thank you, Aya. And yeah, I have a couple of questions. I can start with the first one and then leave the floor to others. The first one is, like, are these embeddings, the known concept embedding and the unknown concept embeddings, trainable parameters during, like,
yeah,
training? Okay.
Yeah. So these are, like, you can think about them exactly like the previous question. You can think about the token embeddings. They're randomly initialized and learned throughout the process. Yeah.
So you haven't tried, like, there is no pre-initialization with, like, semantic embeddings obtained from like anything?
No, we thought about that. We thought about doing, like, initializing from, like, concept embedding themselves based on, like, what we expect them to be. But then we thought, well, the unknown are going to be randomly initialized, so maybe we should just have the known also randomly initialized. And we do learn the token embeddings anyways through the training process, so we might as well learn the concept embedded for this training process. But yes, they are learned throughout the whole process. You can think about them, they're basically NN dot embeds, exactly how you would do token embeddings.
Okay.
Yes.
Giovanni, you can start. You can go with your question, and
Yeah.
have another one later.
Okay, I'll go very quickly. Thank you, Aya, for the talk. I was just wondering, how did you decide for the number of unknown embeddings for the unknown concepts, and how much redundancy do you expect to be in them? Like, is there a sort of sparsity between them that you impose? Like, they have to be orthogonal to each other? How much they can be redundant?
I mean, I'm sure they're very redundant. There is a lot of redundancy there. I will, like, I started plotting, like, the different representation, but, like, what we found is that they don't have a lot of overlapping with the known concepts, which is great. How we decided on the numbers, so we basically did an ablation study, which is, okay, should they be like 10x, 5x, 3x, and or just, you don't want them to be like exactly as the known, because again, there's only 33,000 known concepts, and you can think about the universe of the world that has a lot more than 33,000. So we know that there are a lot, and if you make this known part very small, then basically you won't be able to have any of the clear concepts that oh, one concept to represent something that we can say, oh, this makes sense here. You'll have, like, concept that represents everything and that are very dense and that the model will rely on. But what else? Yeah, so we did ablations, and in terms of accuracy, 3 made sense. If you go over like 10, then the model size just explodes, and we didn't find that it is useful. So yeah, so that's kind of why we went with 3. But the only sparsity constraint we have is then being orthogonal to
to the known concepts. Yeah. Thank you very much.
Oh, okay, the hugging face is
I'm also hitting at a 404.
Just try something. So I'll just try something since I'm here. But yeah, Pietro, you can ask your question.
So meanwhile, I have a question that is, I'm still trying to understand whether the independence loss and the reconstruction loss are actually overlapping to some extent. What I'm saying, like from what I understood from the talk, the independence forces the information in the unknown concepts does not overlap with the information of known concepts, and
Okay, so
the reconstruction.
just
Yeah.
go ahead.
And,
Yes, go ahead, please.
and the reconstruction is to some extent is trying to do something similar. No, it's trying to push information in the unknown part that would allow to all the missing information that is not in the known concept, so that we don't lose information when we get to the embedding before the ML head. So to some extent, I had this feeling that at least partly these two losses were overlapping.
So they are overlapping. So the independence loss is basically, it's a kind of a sort of disentanglement loss. As like everybody here probably already knows that like disentanglement is a very hard problem in machine learning, and like representations are almost never completely disentangled, and a lot of like the concept leakage literature or would find that a lot of the concepts like correlate to one another, or there is like leakage between them because of this disentanglement problem. So this loss just encourages it. Nothing really enforces disentanglement, but what it does is that it kind of basically says, okay, in this particular batch, let's encode something else that is not in the known. Okay, so that's the first loss, what it does. But then the second loss kind of says, so what does it encode? I mean, it can encode anything. So we wanted to encode everything that was in the hidden representation that wasn't in the known. So that's how this reconstruction loss. And if the reconstruction is perfect, then this epsilon residual connection that we had that we technically don't want, right? Because it's basically a black box, so you want it to be zero. If that disentanglement is perfect, then that basically ends up being zero, which is what we want. So these laws help one another. They're not the same. If you remove the first loss, then you basically don't get any clean concept at whatsoever. You'll see, like, if you look at, if we did an ablation where we moved the first like independence loss, you'll find like this, for example, here I was showing this is like this publishing concept, and you would look at the top tokens for the publishing concept, they would have nothing to do with books or publishing. But if you so that's what you have. And if you remove the second one, basically you would find that this epsilon residual has high contribution, because the model really wants its good hidden representation, because it helps it with the language model objective. And then, yeah, so it will rely on the residual more than it will rely on the unknown concept. And then the embeddings for the unknown are not like, no clean embeddings are learned. So we don't know what the unknown embeddings might encode. So yeah, so that's kind of like why we have these two losses. So they are related to one another, but they're more of like helping one another. And if you remove any of them, the whole objective doesn't happen, basically. Which is like the known being separate from the unknown, and both like the unknown encoding things that are in the representation but are not in the known, in a sense. Does that answer your question?
Yeah, to some extent, but yeah, like to go deeper, it would require more time. We can discuss it with more time.
maybe can I add a couple, because I literally wrote pretty much the same question I want to ask, but just thought that then if that's the case, if you need both of them, doesn't that just mean that it's overcapacitated? Like the unknown stuff has way too much capacity, so it's learning redundant stuff. Like in the scenario where you only have enough capacity, the model will have no incentive, that you're very limited in capacity. So the resources the model has that is play when it's sort of optimizing is very limited. Then it has no incentive to encode, re-encode the things that are in the known concepts again into the unknown concepts, right?
Okay, so yes, I agree. But if we go back to like, let me grab the architecture. If we go back to this architecture, remember there is this residual network and the like residual connection. So if you think, okay, if we make the capacity very limited, also like, how do you know the exact right amount of capacity, right? You don't know.
Yeah.
It might depend on like the size of the model. If the model is already really big, then maybe this decomposition doesn't have to be that big. Or it might depend on the amount of data. Like, for example, I'm training here on 1.2 trillion, but what if I trained on like 15 trillion? Like, what is the right amount of capacity? So it's like, actually, I don't know that. Like, I don't know the exact like size. Nobody really knows the exact size, but yeah. So, and you can think about that. The model wants to cheat, right? It wants to, basically, its biggest objective is to learn the language modeling problem. And it can just do that by passing everything through the residual. And if it does that, what happens is, yeah, so it can just completely ignore the unknown head, try to optimize the known one, and just pass everything through the residual. Then we get back to a like completely black box, which we did all of this to kind of like not have. So that's why you would need that other one. And also, like these, if you made the capacity of the unknown really, really small, they would be, right now, I don't think the unknown is like monosemantic by any means, but some of the concepts are actually pretty clean, which is like, again, I was showing like a few examples, and of course, they're like the ones I found that are nice, but you wouldn't. Yeah, you wouldn't find concepts like this. You would find that, and some of the unknown concepts are actually, I look at them and I'm like, okay, what does this concept encode? And I don't know, because it's a ton of things that are random and not related. At least from an AI perspective, I don't know what like the correlation between these concepts. But other ones are like really clean. And I think it's because they happen enough in a pattern in the data that is like, okay, this happens enough that I'm going to assign a concept for it. The model makes that decision. But if you make it very small, then it won't have this luxury to assign anything meaningful to an unknown. It will just use it as if it is like an embedding that has everything, like how you would encode a dense representation in a sense. That's kind of like my take on it. But like, obviously, if you know the exact number, you can design the model that way, but it's really hard to know. And I don't know, like, if it depends on, it probably depends on the transformer size, the backbone transformer size, and the data itself.
That makes a lot of sense. Cool. I do have a lot of other questions, but I think maybe it's better taken offline, just given time. I don't know if anyone else has any other questions. I don't want to take more than everyone's time. Okay, well, if no one else has any questions, thank you so much. This was fantastic. Really, really enjoyed this. And thank you everyone for joining us.